Hi everyone, so today we're going to learn about the concept of half-life. And half-life refers to an amount of time it takes for half of a sample to change into something else. So why is this useful? Yesterday we learned about things that have happened long ago during the history of our planet Earth. Now, it's an interesting question to ask, how do scientists know that something is so old? Well, they can do a test on rocks or fossils that they find and determine how old they are. And this idea of half-life is what helps them do that. So again, half-life is what we're going to call the amount of time it takes, for 1/2 of a sample to, and we're going to use this word, decay. Okay, so to decay means it changes into something else. So let's learn about how that works. You see here a radioactive element. Remember, an element is a kind of material that we have in the world here. You know, the periodic table of elements shows you all the different types of material that everything around us is made of. Well, if something is radioactive, that means that it is not stable. So there's something about the nucleus in the atoms of that element that is not quite right. It is not stable. It does not stay the same forever. So it changes over time. And when it changes over time, we say that that means that the element is going to decay or change into a new element. And here's a picture of that. This description here says a radioactive element. This means that it is unstable, so it will change into something that is stable. So picture this element right here, carbon-14. Carbon-14 refers to a carbon atom that has 6 protons and 8 neutrons in the nucleus, right? 6 plus 8 is 14. That's why they call it carbon-14. Well, over time, carbon-14, which is not stable, will change into nitrogen-14. So it becomes a new element. And you can see that it becomes nitrogen-14 and loses a part of the nucleus. So that is less important. That is something you would learn in nuclear chemistry. But for this year in biology, I would just like us to know that there are some elements like carbon-14 that are not stable. So over time, they change into new material. In this case, carbon-14 becomes nitrogen-14. And that changing process is called decay. Okay? So here's an example. Instead of thinking about just one atom now, let's think about many. Let's say we have this many atoms of our original element, and that you can see is here in red. And after one half-life, that is the amount of time it takes for half of the material to decay. So if we go this amount of time, you can see that half of those red dots have changed into green dots, and the green dot represents the new element. So after one half-life, half of the red dots have changed to green dots. What if we do that same amount of time again? If we wait for another half-life, another amount of time, that means that half of the red dots will change to green dots again. So at the beginning, let's say we have 20 red dots. After one half-life, we'll have only 10 red dots left and 10 green dots. And then after another half-life, we would have only 5 red dots remaining, and then 15 green dots. So see how every time it goes down by half. Okay, every time, however much you have left of the original element, half of it will change into the new element. If you think about that like a graph, it's going to look something like this. These two graphs are showing the same thing. I like this one on the left because it shows us this blue circle like a pie chart. Okay, so imagine at the beginning of, during the lifetime of a living thing, let's say, it has 100% of the original element, which in this graph is represented as blue. After one half-life, which is this unit of time, half of it remains and half of it has changed into something else. You can see that in this example, the original is potassium and the new material is argon. And that is just something that I would have to tell you as a separate fact. Okay, so we have to know that potassium is unstable. It will change or decay into something called argon. So if we go another half-life, another unit of time on the x-axis of this graph, you can see that another half of the blue is gone. Go again, another half of the blue is gone, and that happens every single unit of time. So if we graph it, it has this kind of a shape, okay? It doesn't go down like a straight line like that. Rather, it goes down as a curved line because half of the original sample changes after each half-life. I like this one on the right because it shows us that the parent or original atoms are there in black dots, and the new or daughter atoms are there in red dots. So see at the beginning, let's say we have 20 black dots. After one half-life, we would have 10 black dots and 10 red dots. After another half-life, we would have 5 black dots and 15 red dots. And see how you would just keep cutting the number of black dots that remains in half every time. So why is this important for us in biology? Well, it turns out that scientists have done tests on all these different elements, and they know how long it takes for every element to change into that new element. So anything that is radioactive, scientists have done tests, and they know now how long it takes for something to decay into the new element. Okay, so here's some review for you. Okay, at the beginning of an organism's life, let's say it has, I'll do this like a pie chart. It has 100% of some element, so I'll just color in this whole pie chart. So that's 100% of a certain element. After a certain amount of time, then only half of that would be left. So I'll cover in half of this. So now only 50% remains. After another half-life, only 25% would remain. So see how that gets cut by half every single time. You can also think about that in terms of fractions. So this would be the whole thing, 1 out of 1. This would be 1/2 remains. This would be 1/4 remains, and so on. Okay. So let me give you an example. For a pretend element like the following sample problem has, let's say the element is called rhymorium. Okay, that's different than something like carbon or oxygen or nitrogen. Let's think of a pretend element, so it's nice and easy for us, and we're going to call this pretend element rhymorium. Rhymorium is radioactive, so it decays or changes into this other element called genium. Okay, so rhymorium decays and it will become genium. How long does this take? How long does it take? Well, let me just say that it takes 1,000 years. So if this process of 100% getting cut down to 50% takes 1,000 years, then this next process of going from 50 to 25%, that is just getting cut in half again. And that would take another 1,000 years. So see how every 1,000 years the sample gets cut in half, or half of it decays or changes into something else. So if you want to think of this as a graph where time is on the x-axis and the percent that you have left is on the y-axis, we would start out at the beginning, 0 half-lives, that would be 100%. After 1 half-life, you would have only 50%. After 2 half-lives, you would have only 25%. After 3 half-lives, you would have only 12.5%. See, I cut it in half every time. So then I can draw a line that completes this graph like this, and see, it's not a straight line, it becomes a curved line like this. Okay, so now I could even ask a separate question like, what if you only have 80% of the material left? Well, you could use your graph to figure this out. So I would find 80% on my y-axis and go over to the line here and go down to the x-axis and realize that that's the point that shows me when I have 80% of the original element still there. So I can use this graph to answer other questions that are maybe a little bit more difficult where the math isn't perfectly easy like you see in my example above. Okay, how about some sample problems? So let's go down here and see if we can read through these. So an ancient animal called the flooper has 10 grams of a radioactive element called rhymorium in its body. When it dies, the rhymorium starts to decay into a different element called genium. All right, so we've got this fake ancient animal, a pretend animal called a flooper. When it's alive, it has 10 grams of a radioactive element. And over time, the rhymorium starts to change into genium. So here is the first question to think about. It takes 1,000 years for half of the rhymorium to decay into genium. It takes another 1,000 years for half of the remaining rhymorium to decay into genium, and so on. What is the half-life of rhymorium? Well, if it takes 1,000 years for half to decay, that is the definition of half-life. Half-life means the amount of time it takes for half of the material to decay. So the answer to this must be 1,000 years. Next question. If you find a skeleton of a flooper and discover that it contains 2.5 grams of rhymorium and 7.5 grams of genium, how old is the skeleton? All right, well, remember the beginning of the problem? It told us that a living flooper has 10 grams of rhymorium. So we started with 10 grams. If we go through one half-life, that means that 5 grams is left. If we go through another half-life, that would mean that 2.5 grams remains. Well, there's my the amount that we really do have left. This sample actually has 2.5 grams of rhymorium remaining. So how much time has passed then? That first transition from 10 to 5, that was 1,000 years of time. The next transition from 5 to 2.5, that was another 1,000 years of time. Okay, so if I think about how I figure this out at the end, 1,000 years to go from 10 to 5, 1,000 years to go from 5 to 2.5, 1,000 plus 1,000, my answer is this skeleton is 2,000 years old. Okay, last question. After 4,000 years, what percent of the original rhymorium would remain in the flooper? Okay, so at the beginning, when the flooper is alive, it has 100% of its rhymorium. It has all 10 grams. After 1,000 years, it would be down to 50%. After another 1,000 years, it would be down to 25%. After another 1,000 years, it would be down to 12.5%. And then after another 1,000 years, it would be down to 6.25%. Okay, so you can just cut this in half every time. So see how that was 1,000 years to get from 100 to 50, another 1,000 to get from 50 to 25, another 1,000 to get from 25 to 12.5, and another 1,000 to get from 12.5 to 6.25. Okay, so grand total, 1,000 plus 1,000 plus 1,000 plus 1,000. That is how we get to the total of 4,000. So what is the final percent? That final percent is 6.25%. So that's how Half-Life works. I think you're now ready to do your Half-Life worksheet, which will be posted on Schoology right after this video. Thank you.